Okay, we're recording. Okay, so last time we were talking about global optimization, and this is the big theorem we have, that three conditions you can check. If you check these three conditions, then no problem. There is going to be a global max somewhere in your domain. Roughly speaking, these are the only three sort of problems that can happen, and once you eliminate those three, then everything's fine. All right. Now, let's see an example of this. The big problem that we're going to be dealing with in this first example is how to deal with boundary points. How would we find critical points on boundaries? We're going to actually see a better method for this in section 4.3, which we're going to get to momentarily. I'm just going to show you this one because this is kind of the less sophisticated, more obvious thing to do. But most of the time, this is not the way to go. And I'm going to show you this example partly just for the contrast purposes, so you'll know how much to appreciate Lagrange multipliers when we get to that in a few minutes. Okay, so let's suppose that we're optimizing this function on this this domain. And real quick, let's come back up here and think about, is this domain closed? Well, yes, it is. Look at that. It's less than or equal. So the boundary is included. So this is closed. Let's see. Is it bounded? Well, yeah. It's a subset of a ball. In fact, it is a ball. So it doesn't run off to infinity in any particular direction. So it is bounded. And is this function here continuous? Well, it's a polynomial. All polynomials are continuous. So we know that there's a global max, and we just need to find it. So we start by looking in the interior. We know how to deal with interior. Function's differentiable. We've already established that. And so we take the gradient, set it equal to 0. Go do a little bit of algebra, right? The gradient's easy to compute. Set it equal to 0 gives this point. And so that's our interior critical point. Okay. All right. But again, what about the boundary? And most of what we're going to do in this example is to deal with the boundary. When I got a little too far there. This example is going to work out better than most for the method that I'm showing you here. Even still, it's still not as good as Lagrange multipliers, which we'll see in a few minutes. Anyway, in this example, keeping in mind, we're looking on the boundary. We're looking on the circle there, the unit circle. Well, on the unit circle, x squared plus y squared is 1. Looking at the formula for the function we're interested in, we have an x squared plus y squared. Now that's a lucky break, right? But we can take that x squared plus y squared and just rewrite it as just 1. So you get lucky sometimes. And so we're going to go ahead and do that there. As long as we're on the boundary, as long as the boundary is what we're interested in, we can just treat x squared plus y squared as 1. Okay. All right. So what we're going to do is we're going to deal with the top half now separately from the bottom half. The reason is because the top half by itself is a graph. Being a graph, I can solve for one of the variables in terms of the others, in this case y. And that allows me to then rewrite the function a little bit further. This function is now that. Okay. All right. And the reason that matters is because now this is a function of a single variable. Right? And I can think of this as, as x moves along between 0 and 1, for those values of x between 0 and 1, I can look at this function and ask, with the understanding that I'm actually looking at the point x comma y sitting up above there, right? And I can evaluate the function at those green points as x moves from 0 to 1. And, well, as x moves from 0 to 1, the values that I'm looking at are also just regular old real valued values. And this is a single variable calculus problem at this point, right? I've got a single variable function of a single variable and take the derivative, set it equal to 0, and solve. Now, it's a little annoying. Taking the derivative, you're going to have a chain rule situation and a power rule with a fraction, and annoying. But you come down and you get these two solutions, plus or minus square root of a half. Okay. Of course, now those are just the values of x. And you then plug that into here, and that tells you your corresponding values of y. Okay. Now, this being single variable optimization, again, don't forget you also have to check your endpoints. So keeping in mind that x was going from 0 to 1, our endpoints are plus and minus 1. I said that wrong. Sorry. We're going across the unit disk, so that's from negative 1 to 1. So there's a lot to check there. What we found so far, by the way, we found this interior critical point by setting the gradient equal to 0. Then we found two values of x, and with their corresponding values of y, that gives these two critical points. And then we were reminded, don't forget the endpoints. The endpoints are where x is negative 1 and 1. So we've already found 5 critical points. And we're still not done because we haven't checked the bottom half yet, right? So for the bottom half, on the bottom edge, y is the negative square root instead of the positive. That gives a different formula for the function. Right? Different rewrite for what the function looks like. And so we have to take a whole new derivative and do a whole new blah, blah, blah process, but, taking the derivative, setting equal to 0, and that gives rise to, interestingly, the same values of x, but different critical points now because, of course, they have different values of y. Okay, so plugging in the boundary formulas and turning multivariable functions into single variable functions seems like a good idea, but you see there is a fair amount of tedium involved. We ended up with 7 critical points, right, that we can't eliminate because, they're critical points, right? And so you'd have to check all 7 and see where the value of the function is the biggest. And we don't have to worry about any of this kind of nonsense where, critical points, you have so many critical points, but, there is no maximum value, and so the highest critical point isn't the absolute maximum. This kind of nonsense doesn't happen because we've already checked that this theorem works. So there is a global max, and so in this case, whichever of these 7 is the highest value of the function, that is the absolute maximum. Okay, so again, tedious. You don't want to have to do things that way. So let's talk about the better way to deal with these boundaries. Okay, so this is section 4.3. We come into this thinking about boundaries. In fact, we're going to view this a little bit more generally. I'm going to view this as optimizing a function, but with a constraint. So that constraint might be that you're restricted to looking on a boundary, but it doesn't need to be. It's just any sort of a constraint that you have. So, for example, here's an easy example. Here is a curve in the plane. Right? And suppose you want to find the point on that curve that's the closest to the origin. This isn't phrased in a way that makes it obvious that it's an optimization problem. It doesn't say greatest and it doesn't say least. But you think about it, closest means you want to find the minimum value of distance. And to save ourselves some trouble, I'm gonna look at the square of the distance, because if you find the point where the distance is the smallest, you've also found the point where the distance squared is the smallest, right? So that's just a nice little algebraic convenience. Saves you having to deal with square roots, right? But I'm going to say this is our function that we want to minimize, right? Closest means we want to minimize the distance. All right. There is a constraint. I don't want to find among the entire plane, all of R2, find the point closest to the origin. That's an easy one, the origin. Right? The origin is closest to the origin. But that's not the question. I have a constraint. I am only allowed to look at points that are on this curve. Right? So this is what we mean by a constraint. And so I'm going to call this the constraint function. Let's do it like this. The constraint function is the function whose level set, one of whose level sets, gives us our actual constraint. Okay. So this is a pretty standard example of a constrained optimization problem, right? We want to find the max or min value of some function, aka the objective function, subject to a constraint that we think of as being a level set of what we call the constraint function. So this is the way we're going to set things up. Objective function to be maximized or minimized. Constraint function from the equation describing the rules, what we're restricted to, aka our constraint. How are we doing? Is everybody with me so far? Yes?
How did you decide the objective function again?
Oh, yeah. So this is the way we're going to set it up. Just you'll see why in a few minutes. But when you have a constraint, our rule here is that I need for blah, blah, blah equal to 4, right? I want to set it up as, think of that as there's some function of which we're looking at a level set. And there's a really good reason for this, and you'll see why on the next page. But if you look at this equation right here, right, this equation happens to have already been written as being a level set of something, and that something whose level set you're looking at is your constraint function. Is that cool?
Yeah, I meant for the objective function.
Oh, I'm sorry. I misheard you. What was the question again?
Just like why it's only x squared plus y squared.
Oh, why you don't have to take the square root? This is just a clever move. If you find the point that is closest to if you find the function where distance is as small as possible, well then distance squared will also be as small as possible. That's all it is. It's just that sort of clever. Like if I find the point that that makes f as small as possible, it also makes 2f as small as possible, right? And so tricks like this can be convenient, and in this case we get to avoid square roots, and so that's nice. Yeah. All right, so this is how we set up constrained optimization problems. We have to identify what's the objective function, what's the constraint function. All right, a couple more examples before we get to solving them. Suppose you want to find the biggest rectangular box given a certain required total area. All right, so you've got a certain amount of cardboard, let's say, and you want to make the biggest possible box. All right, well, so this is a constrained optimization problem because there is a function that you're trying to optimize. Right? So volume is what you're trying to make as big as possible. You're trying to optimize volume, but you have a constraint, namely the area. Right? So whatever box you're entertaining as being possibly your best box, well, that area has to be this given fixed amount. So constrained optimization problem. Did everybody see that? Okay, let's see here. Another one, economics example. Suppose you're running a business and you got a limited budget. Sad realities of the real world, right? You only have so much money to work with. And given that, you want to maximize productivity, let's say. Right? Of course you want to maximize your productivity. You're running a business here, right? you're trying to maximize productivity. That is your objective function. That's what you want to make as big as possible. But again, you have a constraint. And that is that limited budget. So however much money you're going to spend on labor, tools, and materials together, that's got to add up to, well, whatever that limited budget is. Right. Okay, so you see constrained optimization problems are all over the place. They're very natural, come up in the real world all the time. Good thing to be able to do. And notice, in fact, this question back here is a constrained optimization problem kind of. We're maximizing this function, and I should say it was on the boundary that we have a constrained optimization problem. The boundary is where x squared plus y squared is equal to 1. And this is the constraint then, and the constraint function is x squared plus y squared. So it's a constrained optimization problem. All right. Okay, so how do we solve constrained optimization problems? Here's the big trick. It's a process of elimination. In fact, very similarly to unconstrained regular optimization problems. I'm going to write down, kind of like we did previously, I'm going to write down a set of conditions, certain conditions. If these happen, then the function's increasing and therefore it's not a maximizer. Now details, we're going to talk about the details here. Sure. But big picture, there are certain conditions that if they happen, the function's still getting bigger. That couldn't possibly be the maximum that we're looking for. Big picture, does everybody see that? How this is exactly like our previous optimization stuff. So it's, again, it's an elimination process. Here's more good news. These three conditions are true almost everywhere in your domain. So this is going to eliminate practically everything in our constraint set. And we'll then be left with a very small number of points that technically we couldn't eliminate. We're going to call those critical points, and we'll deal with them later, right? But the vast majority of the work is going to be done by eliminating most of them with this tool right here. Okay, so let's talk about how this tool works. I do need for both. Oh, reminder, by the way, f. This is our objective function. This is the function that we're trying to make as big as possible, small as possible, whichever it is. I'm going to usually say, I'm going to usually try to maximize arbitrarily. It doesn't really matter. And then we have our constraint function, G. This is the function that defines our constraint set. These are the set of points that we're allowed to actually look at. This is the level set, then. A level set, the appropriate level set of our constraint function. Okay. Alrighty. So, what we need, for sort of regularity reasons, we need both of those functions to be differentiable. You'll see why in a moment. I'm going to assume, again, you'll see why in a moment, that the constraint gradient is non-zero. And I'm going to assume for the moment that the objective gradient points in a different direction. Well, I should say is not a multiple of, mostly that means it points in a different direction, but is not a multiple of the constraint gradient. All right. So this is a picture then of what we're talking about. We have our constraint set. Oh, whoops. Sorry. I'm getting my colors mixed up. Here's my constraint set. I've got my constraint gradient. Don't forget, from chapter 2, we know that gradients are always perpendicular to their level sets. So that non-zero constraint gradient here defines a direction perpendicular to our constraint set. And then we know that our objective gradient points off of that line. So, very importantly then, not perpendicular to our constraint set. Okay, is everybody with me so far? Here's the big trick then. If it's not perpendicular, then it's going to have a shadow down here, projection into that tangent plane. I'm going to call V. And let's look at the directional derivative in that direction. We have a formula for how to compute directional derivatives. Here it is. Gradient dot V. Look at the picture. This dot product, right? Not zero. Right? Positive. That means the function's increasing. And if the function's increasing, then it's not a maximizer, and we win. Does that make sense to everybody? Okay. All right. So, pretty neat deal. And again, this happens most of the time. So we've just eliminated most of the points in our constraint. We're practically done. Right? All we have to do is identify what we haven't eliminated, and then deal with them later. And the ones we haven't eliminated are points where, again, as usual, one of those conditions fails. So one or the other of the functions fails to be differentiable. That's a problem. That's going to be a critical point. If the constraint gradient is zero, well, I mean, I needed it to be non-zero to define that direction. So, problem. And then let's see, the last is if the objective gradient is not a multiple. Right? There's that double negative again. Not a multiple of the constraint gradient, aka when it is a multiple of the constraint gradient. Okay, if any one of these three things happens, we call them critical points. We can't eliminate that as a possible maximizer. And so we have to just, again, check it later. All right. So this is called Lagrange multipliers. A couple of quick comments about this. While it is true that most of the time this is going to be where you find your actual maxima, most of the time, certainly not true all the time, right? And more to the point, again, keep in mind, it's not about finding the right answer, it's about having legitimate mathematical reasoning. And to have a complete, legitimate mathematical argument, you do have to check all three of your conditions, right? And so do make sure, I mean, a lot of students fall into this kind of temptation of saying, boring. Most of my functions are differentiable anyway. Why do I have to even bother checking it? And that's not true. You do have to check. That's part of making the argument valid, right? It does count a little bit on scoring, on exams. Don't think of this as bad news. Think of this as good news. All you have to do is just say they're differentiable, and you just earn points. Right? So again, glass half full. Right? This is easy money. Go ahead and take it. So please do make sure to do the easy parts, for those points, and don't just leave them on the table. Okay, so I have 3 examples to show you. There is a fair amount of algebra in these examples. I'm not going to wade through all of the micro, specifics of the algebra. We don't have time for that, for one thing, but also y'all can totally do that yourselves. So I'm going to hit the highlights that I think are important, and show you where the landmines are. Sadly, there are a lot of landmines in this kind of algebra. It's the nature of the beast. I'm not doing it on purpose. It's part of, it's sort of intrinsic to the material. But I'm going to show you, again, what I think the important points to understand are, and then I encourage y'all to read through the algebra, on your own. Make sure that you can do that algebra as well, of course. Okay, constrained optimization problem. I'm going to find the highest point on a surface. Highest point means this is what we're trying to maximize. There's our objective function, z. I want to make z as big as possible. That's what it means to be highest. We have here an equation that describes our constraint. This equation already in the form of a level set, and so our constraint function is that thing whose level set is our constraint. By the way, it doesn't really matter where the 4 is. If you, for whatever reason, feel this urge to subtract the 4 over the other side and include, minus 4 in your constraint function, totally fine, doesn't matter. An odd complication to throw in for no benefit. But if you want to do it, you can. Nothing wrong with that. Okay. All right, so here's our two functions. They're both polynomials. Polynomials are obviously differentiable. So you just write down they're both differentiable. Boom, you just earned a point. Again, please don't leave those points on the table. Make sure to write that down. Look how easy. There's nothing to it there. Okay, next, looking back at our our things that we have to check. Next, we have to look at the constraint gradient and see if it's equal to 0. A quick cultural note, this is sometimes called the degeneracy condition. There's great reasons for this terminology. Unfortunately, it's well beyond the scope of this class as to why it's called degeneracy. But anyway, you might hear me or others talking about the degeneracy condition. This is the degeneracy condition. Okay, so we need to take the gradient, set it equal to 0, and here it is. There's the constraint gradient. Notice I can rewrite that a little bit. That's going to end up being useful. That's just a little bit of matrix algebra there. And here then is my my degeneracy condition. I want to solve for x, y, z to find my possible degenerate critical points. Now, this matrix, you'll notice, without too much trouble, you can confirm it's non-singular. And being non-singular, any number of different easy points of view from linear algebra confirm that there's only a single solution, and that is the 0 is the only solution. So this x has to equal to 0. How are we doing? Okay. All right, here's the thing, though. A lot of people would label this a critical point. I claim that even though, yes, this clearly solves the degeneracy equation, it's not a critical point. And the reason why is we are only interested in points that satisfy these conditions on the constraint set, right? We are stuck on our constraint set. We're not interested in any way in any point that's not on our constraint set. And this point here, if you plug it into here, it fails. So what we've just found is completely useless and irrelevant. Right? So not a critical point. It's not on our surface, so we ignore it. Does that make sense to everybody? All right, and now to where the fun, the algebra fun begins. We write down our Lagrange conditions, and again, it's just a matter of writing down the gradients and setting them. Gradient of f is lambda gradient of g, and writing it down in coordinates, you get this. Again, we only care about points that satisfy these equations if they are also on our constraint. In other words, only if they satisfy this equation too. So really, altogether, when we say we're looking to solve the Lagrange condition on our constraint set, what we're really trying to do is solve this system of 4 equations. And notice it's 4 equations with 4 unknowns. X, Y, Z, lambda. And this is, like I say, this is where the fun begins. It can get hairy, and that's one of the hard things about writing a test question that uses Lagrange multipliers is making one where this algebra is actually doable. It can be brutal, and sometimes it's 100% intractable. So anyway, there's usually a foot in the door of some sort, though, and I'm going to show you how this one works out. I've chosen the examples that I've got here so that different things will work out at different times. Here's the first one. This equation right here. I can interpret from this that lambda cannot be 0. Right? Because look, if lambda was 0, then I'd have 0 equals 1. That obviously can't happen. Okay. So that's nice information. Now, let me show you why we care about that. Why is it useful for lambda to be known to be not equal to 0? Because then I can divide by it. Very common mistake that students make in doing algebra is to accidentally divide by 0. That's not good, right? You get a lot of wrong answers if you divide by 0. So careful with that. We divide by lambda, which we know to be non-zero, and then these two equations turn into that, in which we can then solve for x and y in terms of z. Now that doesn't actually give us solutions, but at least I can rewrite everything now in terms of z. Okay, all right, then we take these and plug them into there, which then turns this equation into all of this. All right, just notice, so where I had an x, I put what I now know x is in terms of z. Boom, plugging it in. Everybody on board? And it's kind of all over but the shouting at this point. Now you have a single equation of a single variable, just z. Algebra, y'all make sure you're good with this, but the punchline is I now have 2 possible values of z, and when you have 2 possible values of z, that tells you your x and y, and that gives you then 2 critical points. And there we go, 2 critical points from Lagrange multipliers. What do you think? Everybody happy? Okay. Next example. This is the one we previously did without... Oh, yeah. Sorry, question.
So when you're then trying to find the highest point, you just plug both those into...
Yeah.
And then see what's bigger?
That's right. It's got to be one of these. So, yeah, plug them into the function, see where the function is the biggest. In fact, now that I think about it, the function is just z, and so it's easy to do because you see there z is that value, and for this point z is that value, so clearly it's that one. Yeah. Okay. All right, so now you may recall we previously looked at this question to maximize that function on the unit circle. At least that was the boundary part of the previously we were looking at the solid unit disk, but just this is the boundary part of that. And so notice this is what we're trying to maximize. This is our constraint function, because again, that's the function that we're looking at a level set of. And let's see here. First of all, both differentiable. Again, easy money. Don't leave that on the table. Get those points, right? Set the constraint gradient equal to 0. Easy algebra to solve in this case. You get just x equals 0, y equals 0. And again, you got to check and see, is that actually on our constraint set? No, it's not. So again, doesn't count, right? We just found something that somewhere we're not allowed to go, right? So it doesn't matter. This is not a critical point because it's not on the set in question. And then again, looking at the Lagrange condition on our constraint, you write down the gradients, etc. And here we are again with a system of equations, right, that we have to solve. And again, it's different every time. Now, a very common move, possibly the best first instinct move to use when you're trying to solve these, is do what's called eliminating lambda. Namely, you solve for lambda on both and everywhere you can find it. Just solve for lambda. The things that you get lambda to equal to would then have to equal to each other. And we call that eliminating lambda because then you get an equation that doesn't have any lambdas last ended. Because the whole point of these things is that they're both equal to lambda. So that's a nice move, but again, you got to watch out for the dividing by zero thing, right? So it's tempting to say, I'll just solve for lambda here. But notice, in order to do that, I have to divide. Oh gosh, I have to divide by x. Am I allowed to divide by x? Oh gosh, am I? Can I divide by x? How do I know x is not 0? Right? And this is something you have to establish before you go around just willy-nilly dividing by things. Right? Got to make sure it's not 0 before you divide by it. So how do we know x is not 0? Well, conveniently, you can just look at this equation and plug in x equals 0. And it clearly fails. Right? And likewise, you can look at this equation, and this is how it works in this case. You plug in y equals 0. It clearly fails. Right? So from these two equations right off the bat, I know that x and y are non-zero. But you got to get that written down, establish that you know the things you're dividing by aren't 0 before you can divide by them. Again, having done that, you get this equation in which it's easy to manipulate and get that x is equal to negative y. Again, and once you have one of the variables in terms of the others, you can plug in. This then becomes that. Right? And then you can solve for y. And once you know y, then you know x. Quite a bit easier, I think, than what we did, that first time through, when we were doing, all of this, all of this business here was a lot more work, right? A lot more ugly, much more elegant, doing it like this. Okay, all right. Last example, and oh gosh, we have a minute and a half. I'm gonna skip down to the nut here. Constrained optimization, right? Closest requirement, right? So constrained optimization, differentiable degeneracy, blah blah. Y'all have seen that before. Here's the system that we end up with. Here's what a lot of students do wrong. A lot of students will look at this and say, okay, clearly lambda has to equal to 1. Right? Solve for, cancel the x's, what have you. But also lambda clearly has to equal to a 4th, and also lambda clearly has to equal to a 9th. This is a contradiction. Lambda cannot equal to 3 different numbers at the same time. So, no critical points. A lot of students would throw up their hands and say, nothing. And it doesn't work, because when you say that lambda is equal to 1, that requires dividing by x, which you don't know is non-zero. Right? And likewise for all the others. So that just doesn't work at all. In fact, what you have to do here is actually break this down into cases. And so consider, we know x, y, and z can't all be 0. So at least one of them is going to have to be 0. So here's our possible cases, and these overlap, of course. You might have multiple of these variables being non-zero, but at least one of them's got to be non-zero. And so look at these 3 cases, and everything kind of works out nicely in each one. If x is non-zero, then that gives you lambda is equal to 1. For sure. If x is non-zero, cancel the x's, boom. If lambda is equal to 1, you just plug in lambda equal to 1 in there, and you immediately get that both y and z are 0. And if y and z are 0, you can plug that into here, and that tells you that x has to be plus or minus 6. Everybody see that? So we actually got 2 critical points just out of this one case. And then likewise for the other 2 cases that are totally analogous. And so in fact, you can see how dramatically wrong it would have been to just say, there's no critical points. one little oopsie divide by 0 oversight, we would have missed 6 critical points, and that'd be catastrophic on an exam. So be very, very careful. Make sure not to divide by 0 accidentally. And okay. So we're done with Math 219. Don't forget we have a test on Friday, and then final exam on the 18th, I think it is. All right. See y'all Friday. Have a good one.